Okay, we're going to start. Okay, we're going to start. Can you please stop talking? We're going to start now. Okay, we're going to start. Can you please stop talking? Thanks. All right, so we're going to talk about optimization. We're going to make use of all this work we did with critical values. And so with a function, so this is the general idea of optimization. With a function, various values of independent quantity can be chosen, each resulting in a corresponding value of the dependent variable. So if I choose x1 here, that indicates some value for the other quantity. And this is just the general idea of a amount function, right? An amount function, or even a rate function, but so for any given value of the independent, there's a corresponding value of the dependent. So optimization is about what's the best value of the dependent variable. Okay, what's the best value of the dependent variable? And then in order to find that, we're asking then which value of the independent variable gives us the best value of the dependent variable. So this is kind of the underlying principle of optimization. What value of x, or independent variable, will give us the best y, or the best value of the dependent variable, and then what is the value of that best, what is that best value? Okay, so in order to talk about this, the first and foremost, we're going to need the function f. And what's the deal with the function f? Its dependent variable is the value to be optimized. Its dependent variable is the value to be maximized or minimized. And so when we're coming to these word problems, this is actually going to be the centerpiece of the whole problem, is figuring out what the function f is, and then using the function f to figure out what the max value is. So f is this got to be your focus when you come to an optimization problem. Is I got to get that function. I got to get that function whose dependent variable is that thing that they're asking me to find the max or min of. All right. So this is, and I'll keep saying this over and over again because it does not stick easily. It does not stick easily. So the tendency that we see is you just jump into a problem and you're looking for a similar example and taking the numbers and I'm doing this with the equations. Get into a mindset of I'm trying to build a function whose dependent variable is the quantity that I want to find the max or min of. Okay? Second thing is, so first of all, we got to have a function, but then we got to know, is it the max or the min? Okay? What is the best? Is the best the biggest value or the smallest value? And then, is there a restriction on x? Like, is our independent variable does it only make sense in the real world for a particular interval? That's going to be important too. Okay, so then what I'm going to do here in this next part is I'm going to kind of give you a visual, graphical version of these problems, because when you're doing the actual problems, you'll draw a picture, but then most of the work you'll do will be like algebraic. You'll be working with a function, you'll be taking derivatives, plugging numbers in, and all the while you need to have like a mental image of what's going on. So that's what I'm going to try to instill here before we get to doing examples. So here's this function f, and suppose I want the maximum value in my domain from 0 to 30. Okay, so from 0 to 30. So we're starting here at 0, x equals 0, all the way to 30. So if we're just looking at that part of the domain from 0 to 30, can we estimate what the maximum value is and that value of x for which the max occurs? So estimate, go for it. So from 0 to 30, estimate the maximum value and at what value of x it occurs. Go. Okay, where's Jesse Hill? Where's Jesse Hill? Way back there. Jesse, so tell me, did you estimate the max value of y, or the dependent variable?
The maximum reaches 4.25.
She said 4.25, or a little bit more than 4. Agree with that? And at what value of x did that occur? About? Yeah, somewhere around a little bit more than 5. So somewhere he's saying for x a little bit more than 5, right around here, we get a maximum value of 4 and change, right? 4 and a little more than 4. Okay. Any particular? So what's special about that point? X a little bit more than 5 and y whatever 4.25. What's special in light of the conversations we've been having? What's that?
The rate change has a brief pause.
What has a pause? Yeah, something has a pause. What pauses? Yeah, F. The F pause is there, and so what do we call that? What's happening there? Yeah, what kind of? It's a critical value. Critical value is the X value is the critical value. What kind of critical value do we have? Not an inflection point. Local max. Local max, right? It's a local max. Okay, let's do another one. So what about from 10 to 35? From 10 to 35. So now the actual domain is from 10 to 35. And so I want you to find the maximum value of the function when x goes from 10 to 35, and at what value of x that occurs. Talk. Okay, where's Daphne? Daphne Vilches. What do you think, Daphne? So what, from 10 to 35, what's the maximum value of f, and where does it occur?
The maximum value is 2.8 when x is 24.5.
Okay, so she said when x is 24.5. What happened? So right around here, 24, and a maximum value of around 2 point something. Okay, what do we think? Where's Aisha? Aisha. Oh, Alicia, sorry. Wait till you get old. Alicia. Alicia, tell me, do you agree with that? What's that? Why not? What do you say? So you don't think it's 24 and 2 point something? What do you think it is? You think it occurs at 10? A maximum of? 3 point something. So from 10 to 35, do we have a higher value at 10 or at 24? 10, right? So at 10, between 10 and 35, ooh, the natives are restless today, so I need you guys to stay on track, okay? So at 10, we actually have a higher value than we do at 24. So at 24, there is a local maximum there, but the function has a higher value at 10. So what's special about this point? Is this a local max at 10? Is there a local max at 10? So what's special about this point relative to this interval? Is it because it's an inflection point? Is that why we're getting the max? Because it's an inflection point? No. So why is it that is the max? What is special about that point relative to the interval 10 to 35? It's at the end, right? So it's at the starting point of the interval. It's at the starting point of the interval. Okay, let's do another example. Whoops. From 14 to 24. Now let's say 23. So from 14 to 23. And as you're discussing, I'll give you some guidance here. Go from 14 to 23. Maximum. What do you think? Garrett, where's Garrett? Tell me, where is the maximum and what is the maximum?
Is that 23?
Right, at 23,
It's like 2 and some change.
2.5, right? 2.5 at 23. What about there? Is that so? Are there any local maximums in this interval? And because of that, we get the maximum where? At the end point. So now at the end point, right? At the left, at the right end, at the far right end. Okay, minimums now. 0 to 30. Go. Where's the minimum value from 0 to 30? Where's Anna Rude? Anna Rude. Right here. Where's Jacob? Jacob Loeffler. No Jacob? Jack McCardle. Jack, tell me. Where's the minimum from 0 to 30? At 30, okay? Minimum of, what, something like 1 point something, right? Again, the right endpoint of the interval from 0 to 30. One more. Minimum from 7 to 27. Minimum from 7 to 27. Where's Justin Chandler? Justin, tell me, where's the minimum? Or what is the minimum and where does it occur?
At 16 or 17.
Okay. Under 2, right? Around 16 or 17, just under 2. And why did you pick that point? What's special about that point? Local minimum, right? So in this case, between 7 and 27, do I have everyone's attention? Okay. So the local minimum is occurring between around 16 or 17, and it's just under 2. So right there at that local minimum is going to be the minimum of f from 7 to 27. So can we generalize here? Once we pick an interval, if we want a max or a min, what are the possible places where it could occur? What are the possible places where we could get, say, a local maximum? Sorry, we're talking about absolute, right? So given an interval, we're talking about absolute maximum. The absolute highest value the function attains on some interval could occur where? Do we have to go through here and check every single, say we want a local maximum? Sorry, say we want an absolute maximum on this interval. Do we have to go and check every x value from here to here? If we wanted to cut down what we're going to, just the possibilities, if we want to narrow down the possibilities, how would we do that? He said either the beginning point, the end point, or a local max if we wanted the absolute max on the interval. Does that make sense? Does that follow with the examples that we did? Okay. Yeah, so that's the point. That's the point. We can way narrow down the possibilities for where our optimal values can occur to the endpoint and then to the critical points. And if it's local maximum, then we want an absolute maximum, then we just need the endpoints and the local maxes. And if we want an absolute minimum, endpoints and local minimum. Okay, so let's summarize that. So again, we're finding the best value of y. And so now we're asking, what is the list of all possible independent variable values that might give the best dependent variable value? What is the list of all possible independent variable values that might give the best? First of all critical values. And if we were talking about just the maximum, we could say local max, right? But we just can find all critical values. And what else? The starting and ending values of the domain in question, right? And so we can make a list. We can make a list of all these x values, find the corresponding y's, and if we want the maximum, what do? We just, from the list, we pick the biggest value, right? And then we can make a list, and then if we want the minimum from that list, we just find the y value for each of those x values and take the least, right? Okay, but, so that's kind of going to be a general strategy or generally what we're doing in these problems. Again, what's the key? What's the centerpiece? What is everything that's going to revolve in these solutions around the function whose dependent variable is the quantity that we want the max or min of. Every optimization problem is about defining and using a function whose dependent variable is the quantity that we want the max and min of. So if it says we're looking for the maximum temperature, then in that solution to that problem, you're going to be developing a function whose dependent variable or output variable is temperature. Okay, I'll keep reminding you of this until it sticks. This is the mindset you have to be in. So let's look at an example here. What two non-negative numbers, a and b, whose sum is 25, maximize the value of 2a squared plus b squared, and then also minimize? We'll do both for this. Okay, so what entity or thing is going to be the focus of our solution? What mathematical thing is going to be the focus of our solution? Talk to the person next to you. What thing or entity is going to be the focus of our solution? Hint, I've said it many times. And I said it was the most important thing. Okay, Ada, what do you think? As we're doing the solution to this problem, what's going to be the centerpiece or the focal thing for this problem? The equation. Yeah? Any more? Any more detail? A function. Okay, what function? How about Patrice? Patrice here? How about Jesus? Okay. Preston. She said a function. So can you tell me more about the function that will be the centerpiece of the solution to this problem? What's that? Okay, and so the minimum or maximum, is that going to be the independent value of the quantity of the function or the dependent value? The input or the output? The output. We need a function whose output or dependent variable is what? This value, right? If it says maximize this value, then this problem is going to be about a function whose value is that value. And then we're going to maximize or minimize the dependent variable. Okay? So again, a function whose dependent variable is the quantity to be maximized or minimized. And what's the quantity to be maximized or minimized in this case? This. So we need a function whose output is that, or whose dependent variable is that. Okay? So how do we write that? So let's just call it y, okay? We'll call it y. So now the output of this equation, or what's dependent, or the y value, is this value of this thing that we're trying to maximize or minimize. Is that a function? Is that a function yet? No. Why is this not the type of function that we need? It has two variables, right? So we need a function. We could qualify that thing by saying we need a function of one independent variable. So if we called it f of, we got to choose. Are we going to make this f of a or f of b? Doesn't matter. F of a is fine. So if we're going to write this as f of a, that's fine. But then what do we need? We need b in terms of a. We need b equals something with a's in order to write this quantity, 2a squared plus b squared, all in terms of a. And then we'll have a function of a. You see? So now how are we going to write b in terms of a? Well, look, a and b, their sum is 25. So what does that give us? That gives us that a plus b is 25. And so what does b equal? 25. 25 minus a. And if b is 25 minus a, now we could write that quantity as a function of a. Now, part of writing the function is also to write the applicable domain. Remember in all those examples, those graph examples, I gave you a domain. I said x goes from this to this, or this to this. So we want the same thing here. Is there a restriction on a? Does a have a lowest possible value and a highest possible value? Does a have a lowest possible value? What is it? Right, it says non-negative. So a, we could say a is 0. A could be start at 0. And then does it have a highest possible value? Okay, so b could also be only as small as 0, and when b is 0, that's when a is the greatest. Sorry, this is not right. So what's the largest possible value of a? Well, that's when b is the smallest, and a would be 25. So our possible domain here is from 0 to 25. So this is that function. This is the centerpiece of this problem. Right? It's the function whose output, or the dependent variable, is this quantity that we're trying to maximize or minimize. The first half of these problems is usually building that function, and then the second half is using it to find the max or min. First half is building. This is often the hardest part of the problem, is building the function and its domain. That's often harder than the rest. The rest is now using it to find the max and min value of f. Okay, so what did we say? Two possibilities for where maxes and mins, absolute max and min could occur. What was the first possibility? That was the point of all the graphs that we saw. It could be at the endpoints or critical values, right? Local maxes and mins qualify, and then the critical values and the endpoints. Okay? So we'll just do critical values first. Critical values. Are where? How do we get local maxes and mins? What is it about local maxes and mins? How can we use calculus to get them? Critical values are where? Yep, where the rate of change is 0. We get a pause. At the top, we get a pause. At the bottom, we get a pause. And that's where the rate of change is 0, right? Where the rate of change is 0. So we're going to take the derivative. How'd I do? Am I a master? How'd I do? Looks like I have to take it again. What did I do wrong? Chain rule, right? So 2 times 25 minus a to the first times the rate of change of the inside, which is? Times negative 1. Okay, and so now we want to know for where values of a for which this it's 0 or undefined. Okay, so we can. There's nowhere here that gives undefined, right? So that's not a problem. So we need zeros, right? So 0 equals 4a plus 50 minus 2a. But those are both negative, so it'd be negative 50 and plus 2a. Make sure I did the math right. So then we get 6a equals 50. And a is 50 over 6, or 25 thirds. Now, here we just got one critical value. You might have more, but you only have to consider the critical values that are in your domain. So if we get critical values that are outside of the domain of the function, outside of what makes sense, we don't have to check those. Is 25 thirds in our domain? Yes. So we have one critical value, and how many endpoints do we have? 2 endpoints. All right. So now all we have to do is our possibles for max and min. What x values will give the possible, what are the possible x values that would give us the absolute max or min?
0.
What's that?
0.
0? First endpoint? What's the next one? The critical value in the domain, and? So here we have 3 possibilities. And all we have to do now is just find out what the value of what we're interested in is, and then take the highest and the lowest. So what are we going to do? We're going to take f of 0, f of 25 thirds, right? Because it's the output that we want to be maximized, right? We want the output to be maximized. So f of 0, f of 25 thirds, and f of 25. So f of 0, plug in 0, it looks like to me 625. F of 25 thirds, can't do it in my head. F of 25 looks like 2 times, looks like 1250, check my math. And then 25 thirds, I'm going to need some help from a calculator for that, to do it quickly. Anyone got it? 416 and 2/3. Anyone else get that? Let's confirm that. Did somebody else get that for the value of our function at the critical value? Yes? You got that? Okay, thank you. Okay, good. So now we look at these. And what we're interested in, we want to maximize 2a squared plus b squared, and we want to minimize 2a squared plus b squared. So what's the maximum? 1250. Where does it occur? X equals 25, or the right end of our interval. So when a is 25, we get the maximum value of that quantity 2a squared plus b squared of 1250. Okay, what about the minimum value of this expression 2a squared plus b squared? What's the minimum value? The lowest of the three, 416 and 2/3. Where does that occur? At a equals 25 thirds, or the local minimum. Right? That must be a local minimum. If it's the absolute minimum and there's no other critical values, it must be a local minimum. But we're just interested in just the minimum, right? The minimum value of this between 0 and 25 is 416 and 2/3, and that occurs at 25 thirds. Okay, so there's the max value, that's the output, the y value, or the dependent variable. And there's the value of the independent variable where that occurs, right? So you got to make sure you distinguish between those two and can identify which is which. Anybody have a question on, so this is the max, obviously. Where does that max occur? When a is 25. This is the min. Where does that min occur? When a is 25 thirds. Anybody have a question? So that's kind of a simple version of kind of what these solutions look like. Now there's a whole other aspect to these problems in that they're mostly real world problems. This is not, so we're just strictly doing an optimization problem that's just like a pure math problem, doesn't really attach to real world quantities. But that's what all of these, the ones that you'll do for your homework will all attach to real world quantities, and so that adds a whole nother dimension, so let's talk about that. Last chance, questions on this one? So let's just talk about, and we started this conversation Tuesday, but let's just talk about applications of word problems of any type, Here's our advice to you. Orient yourself to the problem first. Don't just look to mimic a similar example. Lots and lots of studies have shown students who succeed on these problems are the ones who are understanding the problem from the beginning, rather than looking for a fast track to an answer. Okay? You're starting by not jumping in and trying to do something, but trying to just understand what's going on. Just trying to understand what's going on. Okay, so here's our suggested approach to this orientation process. First question is, ask yourself, what is going on here? Just step back. What's going on in the situation? What's the goal? Draw a picture. If it's some kind of something visual or geometric, draw a picture if possible. Okay? If you're really serious about this step could take the longest amount of time. Really orient yourself, asking yourself, what is going on in this situation? Rather than just on the mindset of, okay, what numbers do I grab and what do I do? No, understand the situation. Understand the context. Then next, the focus will always be on quantities. And by quantities, we don't mean numbers. We mean like distance, velocity, volume, weight, temperature. Right? That's what we mean by quantities. What quantities are involved? Okay? And then which quantities are changing and which are constant, and then which ones change together. So notice we haven't said anything about what to do yet, or what's the first step in solving the problem. We really want to understand the situation, pinpoint the quantities, and figure out which of them are changing and which change together. And there will always be some that change together. That's the nature of functions and the calculus, right? Nature of calculus is quantities changing together, analyzing those. Now, so this applies to any type of word problem that you'll come to in your math journey, in your math career. Okay? For optimization problems, this goal that we talked about in step 1 the goal will be to maximize or minimize the quantity. That's what we're talking about here. And again, to repeat. After orienting yourself to the problem, the centerpiece of the solution will be a function whose dependent variable is the quantity that we want to maximize or minimize. And I will keep repeating it until that is your focus. So what? You're going to orient yourself to the real world situation. And then as you embark on the solution to an optimization problem, your focus is this function whose output is that quantity we want to maximize or minimize. Okay, so please heed our advice. Students who are less successful at this are the ones who bypass this. They bypass this getting yourself oriented, figuring out what's going on, and you just go right for what's my fastest track to getting the right answer. If that's your mindset, that this is not going to be fun for you. Okay? All right, so let's do a new one. So a rectangular storage space is created against a building using 84 feet of chain link fencing. The fencing will comprise 3 sides of the space, and the building's wall will form the 4th side. The space must not be narrower than 4 feet. What configuration of the storage space maximizes its area? Okay, so what? We want to understand the situation, and so what? Sketching a picture that represents or is consistent with what we're talking about here is going to be a huge part of visualizing this and understanding it. So what I want you to do is draw the best picture you can of what's going on. And so the picture will be an aerial view. It's like you're looking down on the space. Like you're on the edge of the building looking down at the space toward the ground. Okay? So draw the best picture you can. And then while you're doing that, you can talk to the person next to you to make sure that you're understanding the situation correctly. Okay? Go. So this is the orientation phase. Orientation phase, understanding the problem. So draw a picture and talk with the person next to you. Okay, if you have a visual of it now we're going to move to quantities. List all the quantities involved. And again, by quantities, I'm not talking about numbers, right? We're talking about like volume, height, things like that. Okay? Mass, weight, surface area. Okay? List all the quantities. And then once you get the list of all the quantities, which are changing and which are constant in the situation, and which ones change together. So which ones are tied together. If you change one, that the other will change along with it. Okay, go. Okay, so here's a possible sketch. Here's a possible sketch you might have had just without delving into making any conclusions or moving forward to the solution. The building, I'm showing the building here. Here's the building. Okay? And then that's the side of the building, and then the storage space is has 3 sides. The total length of those 3 sides is 84 feet, and then it needs to be at least 4 feet wide, right? Something like that. So that's just one way, purely taking the information from the problem and making a sketch. Yours may have some differences. Yeah.
How do you know what side to put the building on? Like, will it matter if you put it on one of the smaller sides?
Try me again. I don't understand your question.
So, like, where do you place the building? At which side?
So, like, could it be like this? You're saying?
Yeah. So it doesn't matter.
Yeah, it doesn't matter. So it's not going to change. And then so all the quantities are just rotated 90 degrees. So it's not going to change. Yeah. So if you drew yours like this. That's legit too. That's totally fine. Okay, other questions? Okay, quantities. So let's brainstorm on the quantities. What are the quantities you came up with? Where is... Beatong. Yan. Where's Beatong? Is that you? What quantities did you come up with in this situation that are important? So by quantities we mean things like volume, temperature, height, mass, weight. So what quantities will be important in this problem? Okay, give her a second. Is there one that you know that will be important? How about volume? Is volume important here? Okay, so what is something that is important, a quantity like that? Not sure. Okay, how about... Who's next? Quinn. Where's Quinn Marble? Tell me. What did you have a list of quantities? Okay. Length of, so we say like parallel to the building. Okay, give him a chance here. Do you have another one? Okay. So there's two different lengths. The length of the side parallel to the building and the length of the side perpendicular to the building. Area of the space is important. What other quantities are involved? Total length of fencing. I think he's onto something here. Anything else? So we got the length of the side parallel to the building, the length of the sides perpendicular to the building, the area of the space, the total length of fencing. Anything else that anyone else came up with? Yeah.
I'm just like wondering, is it that the length of the side parallel to the building can't be under 4 feet, and the length of the side perpendicular can't be under 4 feet?
Yeah. So it's not really clear, but the implication is that it's both. Yeah. So it would be both, but where it would come into play would be this situation, because your storage area next to a building probably wouldn't, like we wouldn't be 4 feet this way, right? We would utilize space better. We'd be thinking against the building, right? But yeah, so on both ways, we just assume in both sides 4 is the minimum. Yeah, good point. Okay, any other quantities? Okay, which are what about length of the side parallel to the building? Is that a changing quantity or constant? This length right here. Let's call it something. All right, so now let's define it. If it's a changing quantity, then we can use a variable for it, right? So what do we want to call that? I heard x first. But it doesn't matter. It doesn't matter. Any variable. So we're going to call that x. Because as we reconfigure this, we can get different lengths for that x. Okay? What about the side perpendicular to the building? Yeah, y would be fine. I heard z first. Also a changing quantity, okay? Also a changing quantity, z. Okay? Area of the space. Changing or constant? Changing, right? The whole point is we want the maximum area, okay? So the area of that space, we can call it A. So let's start writing these down. X is length of space parallel to the building. Okay, and we better put a unit on it here, right? In Feet. Y is the same thing, but perpendicular. In feet. Okay, A. Z, thank you. That's what we decided, Z. A is area of the space in units. It'll be feet squared. Area units will be feet squared. And then what about the total length of fencing? Changing or constant? Constant, okay? So we don't have to define it. We know it's constant. We know it's 84. So we don't have to, we could set a parameter for that, but we don't need to. We know it's 84. We just use 84. Okay, so which of these changing quantities change together? X, Z, we got X, Z, and A. Which of them change together? So if you change one of them, say if we changed X, does Z change, or does A change, or both, or neither? If you change X, what happens to Z and A? Do they change or stay the same? They both change, right? These are all intertwined. If you change any of those, if you change X, Z and A both change. If you change Z, both X and A change. So these are all wrapped up together. Change one, you change the others. Okay, so we're set up our variables for our quantities. We understand the situation. And so what will be the centerpiece of the solution? Now we're ready to embark on solving this problem. What will be the centerpiece of the solution? Where is Justin Villalobos? Justin here? Okay, Kaylee. Oh, Kaylee's here. What will be the centerpiece of our solution now that we've oriented ourselves to the problem? We're doing an optimization problem. So what will be our focal thing for solving this problem? To maximize what?
The space or the area, the dependent variable.
Right, okay. And so not an equation, but we need a function whose output is, or dependent variable is, area. That's going to be, everything in our solution is going to revolve around a function whose dependent variable is area. The first half, we're going to create that function. Second half, we're going to use it and get the maximum area. Okay? Here we go. I'm gonna erase so I have space now. So we got our variables defined. I'll remake the picture. So we got X, and we got Z, and we want an area function. So call the function capital A for area. No, let's call it something else because we called A the area as a variable. So we don't want to use that as the name of the function. So we'll do F. So the area will be the output of function F. And we need a dependent variable. But before, let's just write an equation for area first before we figure out what the actual function is. So this will often be the pattern is we know we want an area function, but we'll just start out with just getting area however we can. And then we'll morph that into our function. So how do we get the area of the space? That's just a rectangle. It's just going to be X times Z. Length times width, base times height. However you want to, in this case, X times Z is the area. And so if we want to write the function, we could write it as a function of X or Z. We'll just do X. Then what do we need to write now the area function in terms of X only, right? So this is not a function because it's got two different variables. So we're going to need Z in terms of X. In order to get this, it's going to be X times something, right? This function is going to be X times something. And that something is Z in terms of X. So where's that going to come from? Okay, well that's going to come from the fact that the total length of fence is 84. So what relationship do we have between x and z and this 84 feet of fence? What relationship do we have between x and z and the 84 feet of fence? Where is Shandong who? Shandong here. Yeah. What relationship do we have between x, z, and the amount of 84 feet of fence? So let's do 84 equals. How about 84 equals? What does it equal? X plus 2z. So the distance around that thing is x plus 2z. So there's 2 z's on either side and 1 x. And the reason, so we're going to use this to get now z in terms of x to finish our function in terms of only x, right? So z equals 84 minus x all over 2. So now we know what z is. What is z? 84 minus x over 2. Is our function done yet? What's missing from our function? Domain, right? Applicable domain. We need lowest possible value of x and greatest possible value of x. Okay? Lowest possible value of x and greatest. So x So do we know one of those two right off the bat? Yeah, so if we had the very strange case of the storage space that was long and skinny out away from the building, it's probably not what they want, but it can't be any less wide than 4. Now what about the max? When does the maximum value of x occur? When what? But when does it occur? When what situation do we have? When z is 4, right? So when z is the minimum, then we get the most length we can to x. So when z is 4, what is x? 76. Okay, so like I said, half the battle here, or sometimes most of the battle, is getting this function and its domain. We've got the function whose output is area. That's what we want to maximize. It's in one variable, and we've got the domain. This stuff over here, absolutely necessary, but what is it necessary for? It's necessary for the function. So this is like setup work, okay? It's not that these two are of equal importance. The importance is the function, and we to build that function, we're using this little relationship here, 84 equals x plus 2z, to get that function in terms of one variable. So this is supportive of our goal, the main function for the problem. Okay, now what? We want to maximize the area. Critical values and endpoints, right? So critical values and endpoints of the domain will be the possible candidates that would give us the maximum area. So I want you to do that. So, and it might be easier on this function to start by multiplying it out. This is x times 42x here minus 1/2 x squared. That's our area function simplified. Check my math. But I think it's right. Okay. Okay, so we're looking for critical points, critical values, and endpoint values. Find the values of area for those, and take the maximum. So I'll let you do that. Go for it. Did you guys get that? Did you get that? What'd you get for these values? What's f of 42? You can do that. What is it? 982? Did you get 982? 882? 882.
Sorry, that was them one. It's late.
And what about f of 4? Was it 60?
It's 160, yeah.
Both of them?
For the first one, 160.
Okay. Okay, so you should have got the critical value was 42. One critical value of 42. Your endpoints are 4 and 76. If you find the area when x is 42, use the function. The function tells you what the area is when you're at your critical value of 42. You should have gotten 882 feet squared. And then at your endpoints, f of 4, f of 76, what we're finding the areas for these extreme cases. The area when x is 4 is 160 feet squared. When x is 76, 304 feet squared. Some who got that far. Agreement? Yep? Good. Okay? Therefore, How do we maximize the area? What do we do to maximize the area, and what is the max area? How do we configure the shed or the storage area? We're going to do what? Make this how long? That's our x value. We're going to make that 42 feet, and what does that result in z being? 21 each? And what maximum area do we get? 882. Anybody have a question? I want to get another one started. A harder one. Yeah.
X in terms of Z, and go from there.
X in terms of Z.
When you got the area,
I'm not sure where you're talking about.
when you got the area equals X times Z,
Yeah.
can you do X in terms of Z?
F? You mean A in terms of Z?
Instead of Z,
Yeah, well then you'd be finding your function in terms of Z. Is that what you're saying?
Yeah.
Yeah, that's fine. Yep. So he's saying, could we found that area function in terms of Z instead of terms of X? Yes. The process would have looked different with the numbers, but in the end we would have gotten the same dimensions and same area. But yes, you could have done it, the whole thing in terms of Z instead of X. Any other questions? Okay, so the homework is problems more like this, harder problems, okay? They're harder. So I want to at least start and do as much of this as I can, okay? So shipping crate. A square base, box shape shipping crate is designed to have a volume of 16 feet cubed. The material used to make the base costs twice as much as the material on the sides, and the material used to make the top is half as much as the material on the sides. What are the dimensions of the crate that minimize the cost? So if we orient ourselves to this problem, we want to draw a picture first, understand what's going on. So the first thing we notice is that what? It's square-based. If it's square-based, what does that mean about these dimensions of the base? The same. So we could call those x. So we could say x is side length of the base. Now, the height could be something different. The height of the box could be something different. I'll call it h for height. So I'm thinking about a rectangular box, thinking about the quantities involved. I've got side length of the base, I've got height of the box. What other quantities are involved? Volume. Okay, what's the volume? The volume would be length times width times height, or with our variables, x squared h. What else do we know about the volume? Changing or constant? The volume is constant. We want the box to have a constant volume of 16. So in terms of our x and h, it would be x squared h would be 16. Other quantities involved? There's one more very crucial quantity here. Cost of the box. So we'll call that C. So you should see that x, h, and c are all changing quantities. As we change the configuration of the box, different square base side, different height, it's going to give us different costs of the box. So that was the quick version of an orientation to the problem. So understanding that we were building this box, in analyzing the quantities involved. Okay, what will the centerpiece thing of this solution be now? What are we going to focus on in this whole solution to our problem? This is the big takeaway of the day. When you do an optimization problem, the centerpiece of the solution will be a magic word. A function whose dependent variable is, in this case, cost. We want a cost function. So C equals, I'll call it G this time. G of something, all right? So what we need to do first is we need something that gives us cost. So we're not ready to write a cost function of one variable. So we do what we can. We write an equation for cost. Okay, so the cost depends on what side we're talking about. The base costs twice as much per foot squared as the sides. So there's another quantity here, and that's, say, something different. So say S is the cost for the sides per square unit. So to get the total cost for the sides, it's going to be this S value times the total area of the sides, right? Because S is the cost per unit of area. So what's the total amount for the sides? It's going to be, each side is going to be X times H, and how many sides do we have? So that's the area of all four sides times the cost per unit gives you the cost of the sides. 4XHS is going to be the cost of all four sides. How much will the base cost? The area times the cost of the base, which is how related to S? 2S, twice as much. So area times cost per unit area will give you total cost. Here's the area of the sides times the cost of the sides per unit. Here's the area of the base times the cost per unit of the base. What's the top? The area is X squared, and it's going to be half as much to build the top. So that's going to be the general structure of our function. How are we going to get this to one variable, say X? We're going to use our constant volume. H is 16 over X squared. And everywhere there's an H, there's just one. We're going to put it right there. So 16 over X squared is H. And now we've got it in terms of X. S is a parameter, so it's okay to have S in the function for cost because S isn't going to change. That's the set price per unit for the sides. So we can have an S in there. It's not variable. But the rest, everything else will be X. So we're going to plug 16X squared in for H, and then you rewrite that. That'll be the cost function. So as you're packing up, I will do that. 4X times 16 over X squared. S, but don't talk. So here is the cost function. Critical values, endpoints, find the minimum cost.